So, in the last lecture I had described some of the X-ray diffraction techniques, and particularly we are interested in looking at the X-ray diffractometer technique, and we will do one analysis of a crystal structure. Now, so this crystal structure determination, we are going to take up a very simple material which is first of all has a cubic structure, but we do not know whether it is simple cubic or body centered cubic or face centered cubic, and it is a polycrystalline sample which we require for the X-ray diffractometer technique. One can also use powder also instead of a polycrystalline sample, because then each of the powder particles would be single crystals and they will be oriented in some random manner. We will just quickly review the structure factor. So, the structure factor, basically if there are m number of atoms in the unit cell, then the structure factor is given by this equation here, e to power 2 pi I HUJ KVJ LWJ, where H, K and L are the Miller indices of the reflecting plane, while Uj, Vj, Wj are the coordinates of the jth atom, and then there are m atoms. We calculate the structure factor. Why we need to calculate the structure factor? Because we need to find out whether a particular HKL plane, if there is extinction, even though Bragg's law may be satisfied, we will still get no intensity if the structure factor is 0. And we had done the structure factor calculation in an earlier lecture. So, you could go back to that lecture and review those extinction conditions once more. Here I will just put down those reflection conditions without now going through that exercise. And the intensity is proportional to the structure factor multiplied by its complex conjugate. Now, if I take a cubic crystal, I am now looking only at cubic crystals in this lecture, and monoatomic basis. So, there is only one atom in the motif for the basis. Therefore, that particular atom will be sitting at every lattice point of the cubic crystal. So, if it is simple cubic, the atom would be positioned on the corners of the unit cell only. Body centered cubic, corners and the body centered position, face centered, corners and the centers of all the 6 faces of the cubic crystal. So, I have SC for simple cubic, BCC for body centered cubic, FCC for face centered cubic. Now, what are the extinction rules? So, consider the reflecting plane to be 1 0 0, then h square plus k square plus l square is 1. This will be required later, and we get for simple cubic there is no extinction, while the crosses indicate that for body centered cubic and face centered cubic 1 0 0 plane there would be extinction, and we will get no diffraction peak for the body centered cubic and the face centered cubic crystal. And this is because simple cubic, we had shown that all HKL planes allowed, or all HKL planes reflect. For body centered cubic, for reflection to occur, H plus K plus L should be an even number for reflection. And for face centered cubic, H, K and L must be unmixed for reflection. That means, all the indices H, K, L either should all be even or all odd. So, therefore, you can see that 1 0 0, 1 is odd and 0 is considered as an even number. So, therefore, 1 0 0 is a mixed index, and if I add up the indices, the sum is 1, which is an odd number, hence body centered cubic will also not produce any reflection. Now, consider the plane 1 1 0. 1 1 0, as I said, simple cubic would be allowed, while body centered cubic in this case would be allowed, because Now I add up the index 1 plus 1 plus 0, that is 2, which is an even number. Hence, body centered cubic crystals will reflect from 1 1 0 plane. However, the indices are still mixed, 0 being an even number and the other two are odd. Therefore, no extinction for face centered cubic from the 1 0 plane. Now, I am going in this particular order. The reason I am going in this particular order, in fact, I am going in down with increasing values of h square plus k square plus L square. There is a reason for this, that the interplanar spacing for cubic crystal is A divided by h square plus k square plus L square to power half, where A is the lattice parameter. There is only one parameter to be considered for cubic crystal. Now, here as h square plus k square plus L square is increasing, and since it is in the denominator, the interplanar spacing D would be decreasing. So, h square plus k square plus L square, as this increases, the interplanar spacing D reduces. So, I am ordering these HKL planes in decreasing order of the interplanar spacing. Now, consider the 1 1 1 plane. Simple cubic allowed, body centered cubic not allowed, because 1 plus 1 plus 1 is 3 and that is an odd number, and face centered cubic is allowed now. So, this will be the first, if the material was face centered cubic, the first peak will correspond in the diffraction pattern to be 1 1 1 plane. If the material was body centered cubic, the first peak in the diffraction pattern would be 1 1 0, while in the case of simple cubic the first peak would be 1 0 0. This way one can also find out for other HKL indices which are the allowed reflections and which are not allowed. Now, with this table we will now come to the diffraction pattern itself. Now, this is the diffraction pattern that I had shown in the last lecture. Now, this time I have put the 2 theta values for each of these peaks. Now, if I come back to this table, I have put this table in increasing h square plus k square plus L square or decreasing interplanar spacing. So, if you write down the Bragg equation, and this is specifically for cubic crystal that I am talking about, as D reduces, for the Bragg's law to be satisfied, sin theta must increase. So, the first peak in this, which is this one out here, would have the largest D value. So, the reflection would be occurring from those set of planes which have the largest D value, and plus of course, there is no extinction for those set of planes. So, if this was a face centered cubic material, then the first peak should correspond to the 1 1 1 HKL values, because that is where the extinction does not occur. The previous two 1 1 0 and 1 0 0 extinction occurs for FCC. Similarly, if it was body centered cubic, then I would make the first peak as 1 1 0. So, like that we can, by trial and error, I can start introducing the HKL planes, but we will do it in a systematic way, as you will see. Now, let us take all of these 2 theta values and put them in this table in this manner. Now, if I put them in this table in this manner, so I put on the left column the 2 theta values, then I have computed sin square theta values, and now what I did was I have taken the sin square theta values and I have normalized them with respect to the sin square theta value for the first peak, which means all I have done is I have divided the sin square, all the sin square theta values by the sin square theta value for the first peak, which is 0.1355. So, that is all I have done. Now, why have I done this? Let us try to understand the logic for this as well. So, let me write down the Bragg equation. Lambda equals 2d sin theta. Now, I can replace d with the equation for the interplanar spacing for cubic crystals. So, lambda equals 2a upon h square plus k square plus L square to power half multiplied by sin theta. I can write this equation in this manner as well, sin square theta divided by h square plus k square plus L square. What I have done is I am squaring the equation both sides and I am rearranging some of the terms, and this would be equal to lambda divided by 2a squared. Now, this is an interesting arrangement in which I have put the equation. Lambda upon 2a square, if you think about it, this is for a given experiment, it is a fixed value, constant. Wavelength that I take, if it is copper k alpha, it is fixed. The lattice parameter for the material is fixed. Therefore, the right hand side is a constant. The left hand side, the numerator and the denominator will change for different peaks, but the ratio would be a constant. Another way of writing this would be that I can simply write this as sin square theta equals lambda upon 2a square times h square plus k square plus L square. What this means is that the sin square theta values would be in the same ratio as the h square plus k square plus L square value, which means that if I can write this equation by doing the following division, and I can write it as sin square theta divided by sin square theta 1, where basically theta 1 is coming from here. So, this you can imagine that this value is 2 theta 1, the first peak, and on the right hand side I can write h square plus k square plus L square divided by h1 square plus k1 square plus L1 square, where h1, k1, L1 are the indices of the first peak. So, these are the indices of first peak, and 2 theta 1 is the angle for the first peak. So, now how does this help us? So, we will keep this with us and we will do a bit of a hit and trial. So, I am going to select crystal structures. I have got only 3 crystal structures to select, but let me say the first attempt I am going to select the crystal structure as body centered cubic. So, I have selected body centered cubic, which means I must now write specific HKL planes which are allowed for the body centered cubic structure. So, if we come back here, what are the allowed reflections? Well, the first one would be 110, 200, H plus K plus L should be even, remember. Then 211, 220, 2 plus 2 is 4, 310 and so on. Let us write down these HKL indices. So, I have 110, 200 and I am also write down h square plus k square plus L square as well. So, this is 2, this is 4, then I have 211, this will be 6, 220, 8 and I have 310 this is 10, and let me go down to 2 as well, 2, and here this would be 12, and this is for body centered cubic. Now, I write down, I take the ratio h square plus k square plus L square divided by, and this is going to be my reflecting plane H1, K1, L1, which is 110. So, 110 means I am dividing everything by 2, all the sum of the S square plus K square plus L square value. So, the first one I will get 1.00, obviously 2 divided by 2. Next one is 4 divided by 2, that gives me 2.00, 6 divided by 2, 3.00, and you will see the next one would be 4.00, 5.00, 6.00, and we are supposed to compare these two. If this was a body centered cubic structure, these numbers should come very close to each other, but you can see that these numbers are quite far away from each other. Hence, we can say with fair amount of confidence that the material from which the diffraction pattern has been taken is not a body centered cubic structure. So, what we do is, let us try, so I will say do not match. So, let us try face centered cubic. So, we are trying face centered cubic. Let us quickly look at the planes for face centered cubic. First one would be 1, 1, 1, second peak should be 2, 0, 0, the third one would be 2, 2, 0, all unmixed indices I am taking, then 3, 1, 1, 2, 2, 2, and 4, 0, 0. So, let us write down all of these. 1, 1, 1, this is 3, 2, 0, 0, 4, 2, 2, 0, 8, then I have 3, 1, 1, this would be 11, 2, 2, 2, this will be 12, and 4, 0, 0, and this would be 16. Here also we do the same thing. H square plus K square plus L square divided by, this would be H1, K1, L1, the index that we have assigned to the first peak, which is 1, 1, 1, so divided by 3. If we do this, first one of course will be 1.00, then I have, let me put it in a different colors, 1.00, the second one would be 4 divided by 3, 1.33, the third peak now would be 8 divided by 3, so 2.67, then 11 divided by 3 would be 3.66, then 12 divided by 3, 4.00, then 16 divided by 3, 5.33. Now, if we match these two, we find that these numbers are very close to each other. So, they do match. And therefore, in this case we can say by complete confidence that the structure is face centered cubic. And if I go back to my diffraction pattern, I can now assign indices to the individual peaks. So, index for the first peak would be 111, second peak would be 200, third peak would be 220, fourth one 311, fifth one would be 222, and the last one is 400. So, the indexing of the peaks are complete, the structure has been analyzed, and we have found that this is a face centered cubic structure. We will go further with this analysis in the next lecture, where I am also going to look at lattice parameters and a few other things. Thank you.